Hi everybody, welcome to today's lesson. Today we're going to be focusing on the periodic trend of electronegativity. I know we've already discussed this a little bit in class, but just as a refresher, electronegativity is going to be defined as the ability of an atom to attract electrons, and it's measured on a scale of 0 to 4. Okay, that scale has no units, but it is important to note that if you have zero ability to attract electrons, that's the 0. And if you have a really high ability or a really great ability of attracting electrons, that's going to be the 4 is the highest, okay? And so again, why would atoms need to attract electrons, right? If an atom is electrically neutral, what is the purpose of, again, attracting an electron? So similarly to yesterday's lesson about ionization energy, we talked a little bit about the fact that all atoms are looking to achieve the octet rule, okay, or to follow the octet rule. So all atoms are looking to become stable. Now, stability, for the purpose of this conversation, is obtaining a full valence electron shell, which means that we want to have 8 total electrons in the valence shell. Now, there are some exceptions, as I mentioned yesterday, where we are going to have 2 electrons. So remember, helium, for example, is considered stable. It has a full valence shell because our first electron energy level can only hold 2 electrons, okay? So just as a refresher from yesterday too, so again, we said that all atoms are looking to achieve the stability. And so we said that yesterday, remember, metals, okay, tend to lose electrons and form cations, okay? And therefore, when we're talking about metals, we're generally talking about their ionization energy. The fact that they have low ionization energies really aids in their ability to lose those electrons. And nonmetals are going to have, nonmetals are going to gain electrons and form anions. And so our question then becomes, based on electronegativity, why is it that nonmetals tend to gain electrons, but metals tend to lose, okay? So let's go ahead and take a look at our general trend for electronegativity. So electronegativity for our general trend here, let's first talk about going down a group, okay? So our general trend going down a group, so as you go down a group, okay, your electronegativity value decreases, okay? And in just a moment, we are going to talk about why that is, but this is important to note that that's the general trend. From top to bottom, it becomes more and more difficult to attract an electron, okay? Let's go ahead and talk about going across a period. So as you go from left to right across a period, okay, our electronegativity is going to increase. Again, this makes sense if you're thinking about it logically, right? We are looking to attract electrons if we're nonmetals, and therefore it should make sense that they have a greater ability to attract those electrons. Now, again, let's go ahead and just focus on the why and talk a little bit about specifics. So I do want to take a look, as we have been with all of our other lessons, at 3 specific atoms. Let's take a look at beryllium, magnesium, and calcium. All of these are group 2 elements, the alkaline earth metals. They all belong to this group because they all contain the same number of valence electrons, and they all have very similar chemical properties. So beryllium, okay, has 4 protons and 5 neutrons. Magnesium has 12 protons and 12 neutrons. And calcium has 19 protons and 20 neutrons. Okay, let's go ahead and fill in their valence electrons. So beryllium has an electron configuration of 2-2, magnesium is 2-8-2, and calcium is 2-8-8-2. Okay, So just a couple of reminders or refreshers so that, we can really add these into our explanations. Let's think about what we've already learned about these. So again, these are all group 2. Okay? So as you go down a group, what is true of our other trends? Okay? So first and foremost, atomic radius is getting bigger. And we know that because it has an increased number of electron shells. Okay, I reviewed this a little bit in class, but we can also, it's also a good reminder to mention that not only does the atomic radius increase, but there's an increase in the shielding effect, meaning that there are more and more shielding electrons from atom to atom, right? In this instance for beryllium, there's only 2, magnesium, there's 10, calcium, there is a total of 18. Okay, and that shielding effect plays a really big role in our atoms' other trends. And from yesterday's lesson, we also talked about as you go down a group, the ionization energy, okay, is going to decrease, right? It takes less and less energy to remove those electrons because of the shielding effect, because that positive pull from the nucleus is felt less the bigger the atom gets, okay? So now let's go ahead and use our reference tables. Okay, so we want to know the electronegativity values of beryllium, magnesium, and calcium. So again, the beauty of the reference table is that you don't have to memorize it. It is helpful to know the general trend because it will make answering questions a lot quicker, but you also have all of the information here on reference table S at your disposal. So let's go ahead and add in the electronegativity values. Okay, so the electronegativity value for beryllium, okay, according to the reference table is 1.6. The electronegativity value for magnesium, according to our reference table, is 1.3. And the electronegativity value for calcium, according to the reference table, is 1.0. So here you can see that very general trend of going from top to bottom. The ability of an atom to attract an electron becomes less. It becomes weaker. Why is that the case? Again, before we write anything down, I want you to really think about it. Why is it that beryllium can attract electrons more readily than calcium? Well, again, think about the size, think about that shielding effect, think about that positive pull. An electron is negative, okay? And if it's floating around in space, which one of these atoms is it going to feel the greatest attraction to? And the answer is beryllium. Why? Because the nucleus is closer to that valence shell. And therefore, that electron can feel that positive pull to that nucleus more than it would feel that positive pull from calcium. So let's go ahead and jot down our explanation then. Why is it that electronegativity decreases down a group? So the ability to attract electrons decreases down a group because the atomic radius and shielding effect are increasing. Okay, therefore, and these 3 little dots, I use this a lot in this course, that indicates therefore. Okay, therefore, the positive pull of the nucleus is felt less. Okay, so that electron has a harder time feeling the positive energy and therefore does not attract to the larger atoms, or it's less likely to attract to the larger atoms. Okay, cool. Let's talk about our next trend, which is going across a period. So again, I want to go ahead here and I want to go ahead and draw my Bohr diagrams, and I want to use lithium I want to use carbon, and I want to use fluorine. So lithium has 3 protons and 4 neutrons. Carbon has 6 protons and 6 neutrons. Fluorine has 9 protons and 10 neutrons. Okay? Electron configurations are going to be 2-1, okay, 2-4, and 2-7. Now, looking at these, you might say, well, all of these atoms are the same size, right? And therefore, shouldn't they have the same ability to attract electrons? But the answer is no. And again, I want to do what we just did with our last and talk a little bit about what we already know about these atoms here. Okay, so let's take a look. Lithium, carbon, fluorine, they all belong to the same period. So they all have 2 electron shells, okay? As you go from left to right across a period, okay, what do we know about those? We know that the atomic radius is getting smaller, okay? We know that the shielding effect is staying the same, right? Because we have only 2 shielding electrons in all 3 of these atoms, right? Lithium has only 2, carbon has 2, fluorine has 2. Okay, however, what we can see is that there's an increase in the effective nuclear charge, which again is that positive pull from the protons in the nucleus. Okay, so we have an increase in the effective nuclear charge, and we have an increase in the ionization energy. So again, just to review, if you're writing, just pause and listen for 1 second. Okay, lithium has 3 protons and 2 shielding electrons. Okay, carbon has 6 protons and only 2 shielding electrons. And fluorine has 9 protons and only 2 shielding electrons. So, which one of these has the strongest nuclear pull? And it's going to be fluorine, right? Fluorine has that strong nuclear pull because it still only has 2 shielding electrons, but 9 positive protons in the center, therefore pulling everything closer, making it harder to pull an electron away. So I bet you can already figure out at this point why it is then that fluorine should theoretically have the greater electronegativity. But before we go through and explain that, I do want to just prove it to you numerically. Let's look up those values from the reference table. So lithium's electronegativity, according to our reference table, is a 1.0. Carbon's electronegativity, according to our reference table, is going to be a 2.6. And fluorine's electronegativity, according to our periodic table, is a 4.0. That's right, it has the maximum pull that any atom can have. It has the topped out value of electronegativity. Fluorine is the most electronegative element that is out there, which means that fluorine has the greatest ability to attract electrons of any of the atoms on the periodic table. So again, why is this the case? I want you guys to again just really think back to what we were just talking about with that positive pull. So, okay, as you go from left to right, okay, across a period, okay, the shielding, there is an increase. Let's start with there is an increase in the nuclear pull, right? Effective nuclear charge, the pull of that nucleus. While the shielding electrons, well, the number of shielding remain the same. Okay, therefore becomes easier to attract electrons. So again, if you envision an electron in space just floating around these three atoms, which of them is going to have the greater ability to attract it? Is it going to be lithium with this +3 nucleus, or is it going to be fluorine with a +9 nucleus? Okay, the electron is going to be attracted to fluorine with that +9 nucleus. Okay, and so kind of reviewing back with that question, right? I had asked this question yesterday and I'm going to continue to ask it today. Why is it that metals lose electrons and non-metals gain? And now that we've talked a little bit about all of the different trends, we can answer that question fully. So metals lose electrons, okay, because of the low ionization energy, okay, and low electronegativity. So think about it. Metals have very little ability to attract electrons, and in addition to their low ability to attract, the metals have a lower ionization energy, meaning it is favorable with low energy to just get rid of that electron, okay? And nonmetals gain electrons because of their high ionization energy and their high electronegativity. Okay, so nonmetals have a really great ability to attract electrons because of their smaller size and because of their nuclear pull. And it takes a lot of energy to remove those electrons. So that's not super favorable to remove them. So metals lose because it's more favorable to lose than to gain. And nonmetals gain because they have a greater ability to gain, and it's not favorable in terms of energy to remove those electrons. All right, everybody, I hope you guys have a great rest of your day. I will see you tomorrow.